let me spend some time, the last bit of time, talking about time-dependent problems in finite elements. So just a very simple example, solving the heat equation. Du dt is equal to second derivative of u. Okay. And the goal is to see like how does the weak form, or how can we derive a weak form of the differential equation, and how do we get a matrix equation to solve even with time derivatives. The way we do it is pretty simple. You just take du dt minus d square u dx square, multiply with the test function g, which is now a function of space and time. Integrated in space and time. Sorry, let's just integrate it in space. If you integrate it in time, then you'll be discretizing both space and time using finite element. So here, let's talk about, we are still only discretizing space using finite element, and then we get a bunch of ODEs and we solve using our ODE solver. So we only integrate in space. So, but G still is a function of space and time. Okay. This is going to give us, because we are not integrating in time, we don't need to do any integration by parts in time. What we get is okay, so I think, okay, so let's in this case, if we only want to discretize space, G actually should only be a function of space, not time. Okay, so G is a function of space only. All right, but U is a function of space and time. So when G is a function of space only, you can take the time derivative out of this integral, and you get G times U dx, right? So this is the first term. The second term, we do our usual integration by parts. And whatever boundary condition you have to satisfy, we treat it using the same treatment. So let's simplify things a little bit and say we have essential boundary condition, we have homogeneous essential boundary condition. What does that mean? Zero dirichlet, right? Okay, so then the boundary terms goes away. We have plus derivative of G times derivative of U. This has to be 0. Okay? So this becomes my weak form. In this weak form, I have two bilinear forms. So I have bilinear form 1, I have bilinear form 2. So let's denote this as M of G of U. Let's denote this as A of G and U. So I have two bilinear forms. And what I get is the bilinear form, the two bilinear forms, they form a time evolving system. M of G of U plus A of G of U has to be equal to 0. So this actually gives me a chance to discretize the system. So I still enforce my U to be within the space of X with a zero dirichlet boundary condition, and I still have my G to be in the same space. So this case is I enforce my U at any particular time to be in this space, and this space is a function of space only. I'm not considering time. All right. So after now, when I do finite element method, that is basically I choose a X H to be a subspace of this X, and I'm going to have my U of T. Now I'm going to be restricted into this space, and my G is also restricted into this space. So with that, what I have is that d dt of M times a particular Gj, so that is a basis function of the space. Let me actually, sorry, Hj. I have been not very consistent with notation. Hj is a representation of G. If this equation is satisfied for all the Hj's, then it has to be satisfied for all G's. So Hj with a linear combination of ui, which is a function of t now, times gi. I goes from 1 to whatever n, let's say, plus a of the same hj, the same summation of ui gi has to equal to 0, right? And then you pull this summation out of the bilinear form and also the time derivative. No, not the time derivative. You can't pull this out of the time derivative because ui is a function of time. So what you get is d dt of, but you can pull the summation out of the time derivative. I goes from 1 to n, d dt of uit times m of hj and gi plus summation of a of hj and sorry, I keep getting back to g. So this is h. This is the same. If we use Galerkin method, the basis we use to expand the solution is the same as the basis we use to represent the test functions. So this is h. So this is also h. This is h. hi. This is equal to 0. All right. And now look at the time derivative of the product of ui and m of hj hi. If I have a fixed grid, my grid doesn't evolve with time, then I can also have a fixed basis functions, right? If my domain doesn't change, if my grid doesn't change, my hj hi shouldn't have any reason to change. So this m, which is this particular bilinear form evaluated at hj hi, shouldn't change, and I can move this out of this time derivative. M hj hi gets out of the time derivative, dui dt plus summation of I goes from 1 to n, a hj hi. I think I missed my ui here. Times ui is equal to 0, right? And now I can write this in matrix form. I can write this in matrix form. M matrix times du vector dt plus a matrix times u vector is equal to 0. You can see that the A is just our old traditional matrix A, the same A as we use to solve the Poisson's equation. A is the bilinear form that discretizes the second order derivative. I get another bilinear form M. It's a different bilinear form, and that is multiplied on top of this time derivative.